All right, so it's a great pleasure for me to start this data science week. This is the 2023 edition. So as you might have already registered or submit your short talks and everything. Anyways, the mission is you want to diffuse, stay up to date with research and in data science, which is playing a fundamental role in many different sectors, academia, industry, education, and everything. So it is the 5th edition. We're going to have several keynote speakers. Let me go directly to the schedule. So today we start with Professor Díaz. I'll introduce him in a second. Tomorrow we're going to have another presentation, and we start with the workshop. Then we're going to have Professor Tan Wednesday and Professor Aleni as well. Thursday we're going to have a second workshop and Professor Miral Buten. And Friday is basically industry day. So we're going to have a virtual documentary, as it is tradition, and Professor Briganti for the industry time. So if people want to enjoy some interaction, even if just online, you can have access to Slack chat and guided data tab. Okay, so you're gonna receive, you must have received already your password if you have registered. And you click here, you load, you're gonna see stuff around. Let me see if I got it right. Stuff like that. You can see your. Let me write down my name. You go around. You can play here. You're gonna start somewhere. You're gonna see something like presentations. This is Professor Díaz. Talk, right? But you can go around, right? So have fun, talk to people. That's me from another computer. Here we're gonna see our little ChatGPT revolution documentary. And if you guys want to see some of the posters, some might not be yet posted, but I'm gonna do it soon. I think see some posters, videos, and stuff like that. I think we started this idea from nearly 2019. Not 100% sure, but I think we started in 2020 or something. So that's more or less it. So let me stop sharing my screen. Yeah, you're sharing your screen. Stop. And let me introduce Professor Díaz. So Professor Díaz is professor in the Department of Applied Mathematical Statistics and the Mines Institute at the Johns Hopkins University. He has been previously postdoc at Caltech from Professor Chandrasekaran and Prof. He has a PhD from Cornell under Demet Davis. And before that, he did a bachelor and master in actually I think two bachelor in mathematics and system and computing engineering at University of Los Andes, advised by Mauricio Junca and Mauricio Velasco. And then he spent some time also at Google Research. He's interested in optimization. He's interested in optimization, geometry, and statistics. And today he's going to talk about clustering a mixture of Gaussians with unknown covariance. Please, Professor Díaz.
Oh, thank you. Thank you for the introduction and the invitation. So the talk today is going to be about sort of the foundations of clustering, but I wanted to start sort of light with a little bit of motivation, real world motivation. So, let's go. So something that I feel is super important these days in machine learning and artificial intelligence is trying to understand the unknown, because when we don't understand the unknown, terrible things can happen. And this is sort of the underlying motivation of the talk. And I just wanted to give you an example of something that happened to me at a conference in Japan in August this year. So it was a long trip. It took me 22 hours from the moment I left my place to the moment I landed in Japan. And then it took me 4 extra hours to get to my Airbnb. So 26 hours in without sleeping, I got into the Airbnb and the host told me that I needed to register it on this iPad. And so the iPad was there, but it was not turning on. and I was extremely confused and tired. And I saw this red and beautiful button next to it, and that immediately brought me back to the US, where we have this push for help buttons here. And so without thinking much, I decided to press the button without understanding what's going on. It turns out that I was completely wrong. It wasn't for help. Half an hour later, we were here with, it was a fire alarm. So really, this talk is about understanding the uncharted territories in clustering so that hopefully we don't need to call the firemen. So now for the real talk, I want to start by acknowledging my collaborators, Damik from Cornell and Kai Shang from Columbia. So I'm guessing most of you are already familiar with clustering, but so that we have a shared frame to see this, the clustering is the process in which we are giving an unlabeled data set, and our job is to classify the data set into groups that seem similar. This is sort of an ubiquitous task in machine learning, appearing all over the place, from computer vision to network analysis to linguistics. And as you might imagine, we have tons and tons of algorithms and models for clustering. And it's kind of hard to capture all the possible problems that appear in the wild. But we would like to know that at least for sort of simple, nicely behaved problems, our algorithms actually perform well. So the talk today is really going to be about a very simple problem that makes many of the state-of-the-art algorithms struggle a lot. So what's the model? The model is simply a Gaussian mixture. So with probability a half, I'm going to sample from a normal distribution centered at minus mu, some vector, with covariance sigma. And with probability a half, I'm going to swap the sign of the mean. And so it's going to be centered at mu with covariance sigma again. So the picture that you should have in your head is you have two bells, one centered at minus mu, the other one centered at mu. And just to make things a little bit more explicit, we can rewrite this with latent variables, where the latent variables are going to be these y's that are just capturing the signs. So they multiply the mean, and with probability a half, they're either 1 or minus 1. And then we add a Gaussian center at 0 with the right covariance. And so the problem that we want to solve is really just, given the samples, the x's, we want to recover the labels, the y's. Very simple problem. And probably by now you're already thinking, why is this guy talking about clustering if this is sort of a problem that people have solved for a long time? We have k-means, we have PCA. What is interesting about this problem? Well, we're going to impose ourselves some challenges that make the problems harder. So there are going to be two challenges. The first one is going to be, we're going to consider stretch mixtures, which means simply that the covariance that we have is ill conditioned. So usually what people consider is really these spherical mixtures where you have two nice spherical clusters that are separated. And when we have a covariance that is ill conditioned, really what we're doing is just stretching those spheres, and we really have two parallel pancakes. Those two parallel pancakes can be nicely classified still, but actually many of the de facto solutions that we use in practice struggle. So for example, PCA, you might think, what does it do? It looks for the direction of maximum variance. So in this case, the spherical case, the direction of maximum variance is actually this one. So it gives you a classifier that classifies everything perfectly. But once you stretch things a lot, then direction of maximum variance could be the one in which you're stretching, which might be completely orthogonal to the one you're looking for. So this is one of the challenges. The other one is we want to be very efficient, and we want to be very efficient both in terms of statistical and computational resources. Computational resources is natural. We just don't want it to take too long in the computer. Statistical resources are a little bit more nuanced. So let me explain what I mean by statistical resources. And in order to talk about efficiency, we need to understand first what is an easy problem and what is a hard problem. So we need to have some way to measure sort of separation.
Can I ask you a question, by the way?
Yes.
The question is, so are you assuming ill conditioning, or you want to figure it out if it is ill conditioned or not?
I'm not assuming. I'm not assuming that I know anything about. Okay. I just know this. I just know the samples. That's everything I need. Yeah. Okay. All right. So how do we measure separation? How do we measure that something is easy or hard? And so for this, maybe we start with a simpler problem just to define the thing we want. So in one dimension, a natural way to measure sort of signal strength is if we compare the mean separation with the variance. Of course, if we have a lot of variance and very little mean separation, there is a lot of overlap and it's hard for us to classify. But if we have very little variance and a lot of mean separation, then it should be easy. So a natural metric to measure signal strength is simply consider the mean separation squared over the variance. Okay. Now, once we go to higher dimensions, there are many directions in which we can have variance. And so what's the right way to measure this signal to noise ratio? Although there are many directions, there is one particular direction, thanks to the fact that we have two parallel pancakes, that is actually super nice, the direction in which we have separation. And in that direction, we want to measure essentially the same quantity that we were measuring in 1D, this SNR that I defined here. And if you think about it for a while, you realize that there is a nice formula for it, which is simply this quadratic form where I take the mean transpose times the inverse of the covariance times the mean again. If you see, this simply reduces to this SNR when we are in 1D. Okay, and this is the SNR that we are going to measure throughout. If this is large, that means that we have a lot of mean separation when compared to the variance that we have in that direction, and it should be easy for us to classify the problem. If it's small, it should be hard. So with this statistical way to measure separation, now we can talk about efficiency. So we're going to measure efficiency in terms of two metrics. The first one is going to be the misclassification error, which is simply how many mistakes am I making when I'm giving the labels. And the second one is going to be the sample complexity. The sample complexity simply tells us how many samples do I need in order to achieve a good misclassification error. So let me be a bit more explicit here. So the misclassification error of an estimate of the true samples is simply going to be how many labels did I get wrong. And I could be wrong up to a sign, so I'm going to account for that with this minimum here. And I want everything to be normalized between 0 and 1, and so I'm going to divide by n here. Now I talked about efficiency, so what's a good baseline for us to compare against? So our baseline is going to be the base optimal error. If you're not familiar with this, this is simply the best possible error that an estimator could achieve. It turns out that we can characterize this exactly. The best possible error that we can hope for in expectation is actually an exponential of minus the SNR. And this is the same SNR that I just defined one slide ago. In order to obtain this error, we actually would need to know the covariance and the mean. The classifier that achieves this error is super simple. You look in the direction of separation, which is given by this formula here, and you ask, are you on one side of the hyperplane defined by this direction or on the other one? So you ask for a sign. That's it. Super simple linear classifier. Achieves the best possible error. Okay. Now, what's the sample complexity? The sample complexity is the minimum number of samples that we need in order to achieve this base optimal error, at least up to a constant. And what's a good baseline for this? Well, there's an easier problem where I give you this sort of supervised version of the problem where I give you the labels. So you also know the labels. In this case, you can show that the sample complexity, in order to achieve a classifier that has this error in expectation, you will need at least n on the order of d, so linear in the dimension. Now, in order to achieve both of these baselines, we needed to know either the covariance and the mean or the labels. So this leads to a very natural question of, well, I'll have actually two questions. One is going to be statistical and the other one is going to be computational. The statistical question is simply, if I don't know the labels, I don't know the mean, and I don't know the covariance, can I still achieve the best of both worlds? Can I still achieve the base optimal rate, maybe with near linear sample complexity? And the computational question is a natural one. If I can do that, can I do it in a computationally efficient manner or with a polynomial time algorithm? And so the answer, I'm going to spoil the rest of the talk here for you. And what we're going to cover is the answer to these two questions. The answer to the first question is yes. Actually, using a combinatorial optimization problem over the discrete hypercube of ones and minus ones, you can actually achieve this without knowing anything. But in order to have something that is computationally efficient, I said here a combinatorial optimization problem, these tend to be really hard. Actually, if you want something computationally efficient, then it doesn't seem to be possible. You actually have to give up the linear sample complexity here. You need to ask for more samples if you want to be able to do this. Okay, I'm going to be more explicit in a few slides about what I mean by it doesn't seem to be possible. But before I jump into the talk, I sort of wanted to cover very broadly the related work, the things that people have done, because clustering is something that people have worked on a lot. So I wanted to cover why these questions are not answered by the existing literature. So, and this existing literature essentially focuses on, or can be classified into two groups. The ones that assume that they know the covariance and the ones that do not assume that they know the covariance. It turns out that once you know the covariance, the problem simplifies a lot. So if you know the covariance, you can actually transform your data so that you get a new problem where the covariance of your new data is an identity. So essentially, you just make a change of basis with this covariance, and you're able to get to the spherical case again. So this is happy land. Many people have studied this problem, and there are many very nice ideas within this realm concerning PCA, the EM algorithm, k-means, semi-definite relaxations, and all sorts of very, very nice ideas. And the sort of broad message in this realm is that you can obtain the error that you want, so an exponential of minus the SNR with linear sample complexity. So this is exactly what we want. But the caveat, of course, is that you need to know the covariance. And a priori, this is maybe a harder problem, but we could ask, can we estimate the covariance and then try to solve the problem? So a natural idea is just let's estimate it using the data that we have. So if we were to get an empirical covariance, what would we get? We would get the covariance that we want to recover plus some rank 1 matrix. It turns out that demixing a rank 1 term like this is really hard unless we assume more about the two terms that we have in here. We are not assuming anything. We are in the general case. And all the approaches that I know for doing this actually require much higher sample complexity, much higher than linear. So those are a no-go for us. And so there is this other line of work that considers an unknown covariance. And this line of work can also be classified into two. The ones that are sort of happy with higher sample complexity, and the ones that do not consider the same kind of SNR. So there are many works in sort of the theoretical computer sciences community that consider this problem, but they are happy with just polynomial sample complexity. They have some algorithms that solve even harder problems, and this is just a particular case for them. But once you go and read the papers, I remember at some point I opened one of those and went and see the actual exponent that you get here. It's common to have really large exponents. The one that I saw was like d to the 100. So it's not practical, and although it's beautiful from a sort of mathematical theoretical perspective, it wouldn't be practical. So we really want this d to be smaller. Now, a different approach has been to consider another SNR. So as I said at the beginning of the talk, when defining this SNR, there are many directions in which we can consider the variance. We consider the direction that gives us the separation, but we could also consider the covariance in the variance in the worst possible direction. The variance in the worst possible direction when compared to the mean separation. So here we have the mean separation over the worst possible variance, which is just the spectral norm of the covariance matrix. In turn, what you can prove with this SNR is that many methods actually achieve an error of an exponential of minus s with this new s with linear sample complexity. So almost what we wanted, but with this different s. And there are many works, beautiful works again, that use this s But this has sort of a downside, a very important downside, and it's that it's not capturing things that are very stretched. So, for example, if I were to consider two clusters that are spherical and well separated, then the worst possible covariance is small when compared to the mean separation. But if I consider something two parallel pancakes, then the worst possible covariance is actually going to be very large when compared to this mean separation. And so S is going to be small. We don't have a lot of signal. We cannot see a lot of signal. And you can actually see very simple examples. Here I have something in 2D with a diagonal matrix, and the mean is going to be 0, 1, where S actually is 1. So there is not a lot of signal in the noise, but the SNR that we defined is 100. So the error that we can achieve is like exponential of minus 100. And in general, you can prove that the SNR is always larger than S. So whenever there's separation with respect to this S, there's going to be a separation with respect to the SNR, but not the other way around. So just to summarize, the existing literature doesn't cover our questions because either they need to know the covariance, or they have higher sample complexity, or they have this suboptimal dependency, suboptimal dependency on the signal to noise ratio. And you might think, okay, this is just maybe an artifact of the proofs. Hopefully PCA and k-means and all the methods that people are using in the literature actually can tackle this type of stretch problems. And just to convince you that it's not only an artifact of the proof, let me show you a small numerical example using fashion MNIST. So if you're familiar with a NIST, those are pictures of small handwritten numbers. This is just small pictures of clothes. So what we did for this experiment is we subsampled 1,000 photos from this data set of two classes, t-shirts / tops and pullovers. And we classify them using k-means, very popular algorithm for clustering, and one of the new algorithms that we propose in this work. So here I'm showing you the data set projected onto 2D. And we can see very clearly that these are the true labels. We can see very clearly that we have two stretched clusters. And if we run k-means, the thing that we get out of it is pretty much orthogonal to what we were looking for. If we run our new algorithm, it gives us something that is very, very close to the original labels. If we measure the misclassification rate for these guys, it's going to be 44.7%. Thanks to this error up to the sign issue, the maximum possible misclassification rate is actually 50%. And our misclassification rate is 7.1%. Okay, so hopefully by now you're convinced that this is a true issue that we should try to tackle. And so now I can present the bulk of the work. And the agenda for the day is going to be, first, I'm going to introduce this combinatorial optimization problem that solves the problem. This is what I'm going to call the max cut formulation. This turns out to be really hard to solve. So later we're going to see an efficient spectral-based method to solve the max cut formulation. And finally, I'm going to talk about this thing called a statistical to computational gap. All right. So let me start with the max cut formulation. So in order to come up with a good estimator, sort of the key insight that we had was that we discovered that the SNR actually has some invariance. What do I mean by this? So let's assume that you have a transformation that goes from RD to RD that is invertible, a linear transformation. If you apply the transformation to the data, you can be making everything spherical, or you could be rotating things or scaling, whatever you want, provided that is invertible and linear. If you do that, then the SNR of your data is not going to change. So the SNR of the original data is the same as the SNR of the transformed data. In turn, what this means is that any estimator that depends on this SNR has to be invariant under these transformations as well. So we need to look for an estimator that is invariant under these transformations. The fact that we have this invariance actually allows us to think of the data however we would like. So we can transform the data however we would like, although in practice, our algorithm is not going to do that. for the analysis, we can think of the data transformed in a nice way, just for the analysis. And so here, what I'm going to give you is a result that essentially gives you one of these nice versions of the data. So we prove that if we were to organize the data as the rows of a matrix, there is a transformation such that the transformed data looks as follows. The first entry, we have the labels that we want to recover, plus a little bit of noise. All the other entries are pure noise, okay? Where the pure noise is IID Gaussians. And the amount of noise that we have in the first component is sort of inversely proportional to the square root of the SNR. So a lot of SNR, a lot of signal to noise ratio, would make the amount of noise that we have here very, very small. Again, we cannot actually find this transformation. Finding this transformation is hard, but we can use this just for the analysis and for mental experiments. Okay, so again, intuition, every data point has its label in the first component and noise everywhere else. And with this intuition, now we can think of what's the easiest estimator that a statistician would use. Well, that would be the maximum likelihood estimator. And it turns out very nicely that the maximum likelihood estimator in this case is invariant under these invertible linear transformations. So let me just define what this is. So let's define H to be the projection onto the range of the data. Again, imagine that I have a matrix that in each row has one data point. I have n rows and d columns. Since I'm going to have n being larger than d, then the range of the data is going to be a d-dimensional subspace in an n-dimensional subspace, which is larger. And this is just the projection onto the data, onto that range. And so we proved that the MLE of this problem is actually a discrete optimization problem over the hypercube that looks as following. Let's y be a variable that has entries 1s and -1s, and consider the quadratic problem, the quadratic form y transpose hy. It turns out that by maximizing this, we are simplifying the MLE. This has a nice interpretation from graph theory, where in graph theory, often we are interested in finding a max cut, which is simply classify the nodes of the graph in such a way into two groups, in such a way that the number of edges going from one group to the other, one color to the other, is maximized. It turns out that you can write this problem if you substitute here h by the Laplacian of the graph. This is exactly what this is finding. This is not sort of the intuition that we're going to follow. The intuition that we're going to follow is going to be metric rather than graphical. So one way to see this is actually as a minimization problem. We can rewrite this problem equivalently as the problem of minimizing the distance between the hypercube and the subspace generated by the image of H. And so the picture that you could have in your head is I want to find one point in the hypercube such that the distance between the hypercube and this image of H is minimized. Now, thanks to the previous slide where I had this canonical form, we know that the image of H is really generated by, it's really generated by these vectors, where one of the vectors is pretty much the labels that we are trying to recover, plus a little bit of noise, and all the other vectors are just pure noise. So hopefully, since this is the only planted vector here and everything else is random, then the thing in the hypercube that is going to be closest to the subspace is really this y star. That's sort of the intuition for this method. It turns out that this intuition is correct, and we were able to prove the following. So I'm going to present everything in sort of an asymptotic fashion, very classical in statistics, but we can write everything in a non-asymptotic way. It's just that this way is easier to present. So let's imagine that n is that the dimension is increasing, and moreover, the number of samples grows almost linearly with the dimension. And the SNR also has to increase. So everything is growing to infinity. Then we can show the following two things about the max cut problem. I'm going to show something about the expected error and something about the probability of having zero error, which is stronger than the expected error. And for each one of those, I'm going to have a condition on how large this SNR can be. And I'm going to come back to why I need those conditions in just a sec. So let's assume that the SNR only grows logarithmically in n. In this case, we can show that the expected misclassification error actually decreases as an exponential of minus the SNR over a constant plus something that goes to 0 as the dimension goes to infinity. So this is pretty much the base optimal error up to this little O term here. Now, if we assume that the SNR grows faster than logarithmically, and in particular, it grows like 2 plus epsilon for any epsilon you want, then the probability of this error not only being small, but being exactly 0 goes to 1 as n goes to infinity. So with high probability, we have a perfect classification. There is a question?
So my question is about this, like in your linear transformation, let me think it this way. So I remind the case of a normal distribution. Okay, normal distribution you can use to distinguish between normal distribution, something like the hyperbolic metric. So now what I'm wondering here is that two things. One, if there is something geometrical that can be taken into account other than something combinatorial, and two, if instead of trying to figure it out both the variance and the mean at the same time, one can try to verify, one can try to estimate a combination of them, which I don't know.
We're not trying to estimate. This is not parameter estimation. We're just trying to estimate get a good estimator, an estimator that would give us this SNR.
Yeah. Let me rephrase that. Let me say it this way. If I consider the geometry which comes out from the normal distribution, does it give you a better indication on how one can set up the optimization problem you're talking about? What I'm saying is that there might be, in some cases, some combinations of parameters which are better parameters than directly the sigma and the mu as something that you need to do your classification problem.
But so I'm a little bit confused because I don't know of. Okay, so you're saying your question is not about parameter estimation, but I'm not estimating the parameters. I'm just finding a classifier. So what's your question exactly?
My question is this. So let's say you have the case. So you're trying to do, your clustering algorithm. And your clustering algorithm, you're not assuming that your covariance matrix, something like that. You don't know your mean. You want to distinguish between the two, the two groups. Now we're talking about transformation. Transformation, which tends to spherical to stress.
So I'm not using the transformation, right? I'm not coming up with the transformation.
Okay.
I'm just using my data. The transformation I was just using as a sort of mental experiment to know what's going on for the analysis, but not for the algorithm. I never construct the transformation.
Okay, thank you.
Okay, and your other question was about the combinatorial problem. We're going to try to get around having something combinatorial in just a sec. Okay, so a couple of remarks of this. The first remark is that we truly obtained the base optimal error up to this little O term here. The second remark is that the reason why we need this log n, or why this log n is important, is because separation holds with high probability, even only if this SNR is greater than 2 log n. So one can show that there is a linear classifier that achieves perfect error with high probability, even only if this SNR is greater than 2 log n, strictly greater. So what this is telling us is that our max cut problem actually achieves perfect error with high probability whenever it appears. So it seems to be really good. The only downside of this, of course, is that the best known algorithms to solve these max cut problems actually take exponential time. Maybe some of you in the audience have seen max cut instances before, and there are some that are actually not that hard to solve in the sense that we have good relaxations that give you good approximations. So a natural idea is consider spectral relaxations, where instead of having a hypercube, we have a sphere of the right size. It turns out that this is a projection matrix, so the leading eigenvector is not unique. So this is not giving you any information. Something that is more fruitful probably is considering semi-definite relaxations. This was an idea introduced by Gormans and Williamson in '95, where they came up with this semi-definite program that is a relaxation of the problem that I described. And they have good approximation guarantees for this algorithm. The only issue is that the guarantees do not apply here, since H is not a Laplacian of a graph with positive weights. Nonetheless, you can try to apply this and see what happens. We're going to come back to this idea in a little bit later in the talk. Okay, and so also trying to answer the question that was just raised, how do we get around having something that is combinatorial in nature? And so we tried to do this for a long time, and we came up with this algorithm that is sort of based on many ideas in modern non-convex optimization, which is based on splitting the algorithm into two. So here we have a non-convex problem where the objective is convex, but the constraints are non-convex. And so we split the algorithm into two parts. The first stage is going to initialize the algorithm, find a point that is close to the solution, maybe not exactly the solution, and then run a local refinement method, an iterative method similar to, say, gradient descent that actually gets to the exact solution. Okay. Generally, the first stage is based on a spectral method, and it's a little bit harder to sort of interiorize. So let me start with the second stage, which for us is going to be projected power iteration. So the idea here is we want to solve this almost an eigenvalue problem, but for eigenvalue problems, we have a constraint over the sphere instead of over the hypercube. But we can use inspiration from problems in linear algebra, from algorithms in linear algebra. And what they do, the most simple algorithm to compute the top eigenvector of a matrix is power iteration. What it does is simply it multiplies by the matrix and then normalizes to 1. So it normalizes the vector or just projects onto the sphere. So multiplies by the matrix, normalizes the vector. That's it. Here we're going to do something similar, but instead of projecting onto the sphere, we're going to project onto the hypercube. And so here's the algorithm. We're going to iterate, and at each iteration, we're going to multiply by the matrix H, and then take the sign, which is just component-wise signs, which is just projecting onto the hypercube. This is simply alternating projections. We project onto two different sets. Here we are projecting onto the hypercube and projecting onto the image of H, because this is a projection matrix. This is an algorithm that has been studied in optimization for a while, especially in the context of convex optimization. It was proposed by von Neumann more than 70 years ago. So hopefully it is a decent algorithm to use here. And then in order to initialize, we need a good, here I have the initial guess y0. We need a good initial guess. So in order to get that initial guess, we need a spectral algorithm. And this one is a little bit harder to parse, but it's simple in spirit. It does three things. Step one, it transforms the data, essentially normalizes the data using the empirical covariance. We get new data points, WIs. Then we compute a weighted sample covariance. So a sample covariance, we just have this part here, but we add some weights. And then from this sample covariance, we compute the eigenvector associated with the smallest eigenvalue. And we use that eigenvector to classify. Again, we only have a simple linear classifier, multiply dot product with the vector, and then take the sign. The intuition here, the key insight, is that it turns out that once we have enough samples, this S concentrates a lot around a matrix that looks like an identity minus a rank 1 matrix. The minimum eigenvector of this matrix is this guy here. So by computing the least eigenvector of S, what we're trying to do is approximate this vector V star here. In turn, one can show that this V star gives an optimal classifier for these guys. Again, this is hand-wavy intuition, but the key idea is that we are trying to estimate this V here, V star here. So if we combine the two methods, so let's say that Y hat is the output of first running the spectral method and then using the output of this method to warm star the alternating projections algorithm, then we can say the following. We can actually say that in a slightly different regime, where n grows now quadratically with d, we solve the problem. So we obtain exactly the same guarantees as before, but we are in this quadratic sample complexity regime. And for a while, we thought it's just as being silly, we couldn't find the algorithm, but there should be an algorithm that could get rid of this 2 here. It turns out that it seems like there is no such algorithm, and we just couldn't find it because it doesn't exist. And so this is an instance of what people are now calling a statistical to computational gap. So what is this? What do I mean by that? Well, so far we've established that when we are in the stretched case, we have a landscape that looks pretty much like this. If we don't have enough data points, then even in the supervised case, it's impossible to recover. But after we have enough samples, which is higher than linear, then it is statistically possible to solve the problem, meaning that our data contains all the information that we need in order to solve the problem. Now, extracting the information from the data might take us the age of the universe. So if we want to have something that is computationally tractable, that runs in polynomial time, we actually need to go up in the dimension. And so the number of samples has to be quadratic in D. And this is what we saw with the spectral algorithm. But you might ask, is there something in the orange region, something in between, for which we get a decent method? And we conjecture that actually this is not possible. There is no polynomial time algorithm that performs better than a random guess within the orange region. So you might as well just throw a coin per each data point and get the output of the coin. That would be as good as any polynomial time algorithm. This to me, although it's only a conjecture, this is beautiful because there is no statistical to computational gap when we have a spherical mixture. So when this S is actually large, this gap just closes. But once we stretch things, then everything becomes harder. You might ask, how do you prove a conjecture like this? Proving a conjecture like this is hard because we have no polynomial time algorithm, and everything here is random. It's not like in classical complexity theory, where you look at the worst possible scenario. Here we are looking at the average case scenario. Nonetheless, people have been collecting sort of different ways to come up with evidence to support these claims. And usually they come in the form of, we can prove that no algorithm from this class of algorithms, of polynomial time algorithms, can perform better than a random guess. And so what we did was essentially collect different pieces of evidence for, using these tools developed in the literature. So today I'm going to show you 3 pieces of evidence. The first one is probably the most fun. It's just numerical evidence. We tried a bunch of methods and saw that actually you need a quadratic number of samples in order to recover. The second one is going to use a reduction from a hard testing problem that cannot be solved with spectral methods. So this is one of the classes of problems that we're going to consider. In this of algorithms, in this case, we're going to see that actually the theory is telling us or suggesting that D square is actually the limit. We are going to prove another lower bound for some of the square relaxations, which are very popular in the literature these days. They're super effective for many problems. But we're going to show that actually those SOS relaxations failed whenever n is smaller than d to the power of 3/2. Slightly worse than what we would want, but nonetheless evidence. So let me quickly tell you about the numerical evidence. So for this, what we did was we tried to measure the recovery frequency for a bunch of different parameter configurations of n and d. And we made sure that for every parameter configuration, the signal to noise ratio was 3 to the log n. So there is strict separation with high probability, very high probability. So here's one plot of this recovery frequency. This is a log-log plot. Sorry if this is too small. The y-axis is log of n. The x-axis is log of d. And for every pixel you see in here, essentially we drew 10 problems. And so how many of them did we recover with the max cut formulation? If you see white, that means that we recovered all of them. If you see black, that means that we didn't recover any of them. And here we see that there is this very sharp phase transition around this curve that has slope 1. Since it has slope 1, that means that we have linear sample complexity. Now, this is a log-log plot. If I run a polynomial-time method, for example, the semi-definite relaxation given by Gomez and Williamson, we see that there is also this hard transition here, but the slope here is 2. Again, since we have a log-log plot, this means that we have quadratic sample complexity. We did the same for many other algorithms, including the one that we studied in theory, the spectral closed alternating projections method. And for all of them, we see pretty much the same phase transition with quadratic sample complexity. We did it for other algorithms that I'm not going to talk about, such as the EM algorithm. But the pattern is the same, quadratic sample complexity whenever you have a polynomial time algorithm. So that's for, excuse me, how many time do I have left? We started a little bit late, but 5 minutes? It's hard to see. Okay, 5 minutes. And so now let me jump into the theory part of the evidence.
15 minutes, 10 minutes plus, 5 minutes plus questions, so you can do 15 in total.
Oh, okay, okay. I was gonna get rid of part of the talk. Okay, sounds good. So now let me jump into the theoretical evidence. So something that people do in classical complexity theory to prove that something is hard is they have a problem that they believe to be hard, like 3-stat, and what they do is they get a reduction from that problem to the problem that they are trying to prove that is hard. So that way, through the reduction, if you find a solution to your problem, that would imply through the reduction a solution to the problem that you believe is really hard. You can do the same thing here, but now we are not talking about the worst case scenario as in classical complexity theory. We're talking about the average case scenario, in which case not only you need to reduce the problem, you also need to reduce the distribution. So what we're going to do is sort of reduce from a hard testing problem, a hypothesis testing problem that is believed to be hard by the computer science community that has been studying these average case problems for at least 2 decades now. Okay, so what's the testing problem that we think is hard? You're going to probably right away relate it to something that we saw at the beginning. So the testing problem is very easy. We have a matrix. We observe a matrix that has the same dimensions as the dimensions that we are considering. So number of samples times the dimension. And we want to come up with a test that does hypothesis testing and tells us either null or alternative. And the null hypothesis is simply going to be everything is Gaussian. The alternative hypothesis is going to be actually within these Gaussians, we have a planted vectors of 1s and 1 minus 1s. And so it's going to look like this. So X is a matrix that has the planted vector. X tilde is just the planted vector and a bunch of noise everywhere else. Of course, if it had this form, we only need we would only need to check the first column and we would be done. So to make it truly interesting, we multiply by an unknown rotation. And our job is to tell whether it's pure noise, pure Gaussian noise, or there is a planted vector within our matrix. And of course, we want to have a small type 1 plus type 2 error. So if you remember from Stats 101, type 1 error is what's the probability of saying alternative when the null holds, and type 2 is what's the probability of saying null when the alternative holds. Okay, now why is this a hard problem? Well, recently, a couple of guys from theoretical computer science proved a lower bound for spectral methods. The spectral methods are essentially methods that construct a matrix from your data and use the spectrum of the data to decide whether or not you're in the null case or in the alternative case. So they consider a family of spectral tests. The details here are completely immaterial. This is just a lower bound that tells us that this is hard, but I'm going to quickly give you the details. So let's fix a degree P, and we're going to construct a matrix from our data that is going to be a symmetric matrix that has size at most n to the p, with polynomial entries in each one of the coordinates of degree at most p. Then we consider a very simple test that simply measures the spectral norm of this matrix M. And if the spectral norm is smaller than some threshold, it says null. If it's larger, it says alternative. Spectral methods like this are believed to be super powerful in the computer science community because there are many, many problems for which we use spectral methods and they tend to work very well. We even saw at the beginning of the talk, when I introduced the efficient algorithm, that we were using a spectral method constructing a matrix that had polynomial entries on the data. Okay, so very recently, Mao and Wine proved that in the regime that we're interested in, any test that coming from this family actually cannot achieve a very small type 1 plus type 2 error. We would expect this type 1 plus type 2 errors to decrease exponentially, but it decreases at most polynomially, where we have here a C that is constant, we have a polynomial bound, lower bound, where the C here, the degree, is going to be constant. All right. And so what we were able to prove is that if we were to solve our problem, the clustering problem, then we could come up with a test from the solution to the clustering problem that would give you a test that has type 1 plus type 2 error that has arbitrarily fast decay. So let me just formalize this. So assume that we are in the regime where n is linear in D and that the SNR is growing logarithmically times some sequence here that depends on n. Then there is an estimator for the clustering problem. And there is an estimator for the clustering problem that achieves the base optimal error that we want. So assume that we're actually solving exactly what we wanted in the regime that we wanted for the clustering problem. Then we can come up with a simple test just using this estimator that achieves a type 1 plus type 2 error that decreases like a polynomial on this sequence. So if you were to have an SNR that is arbitrarily large, which is the case for the problem, the testing problem that we have, in that case, there is no noise in the first component. So this can be arbitrarily large. Then we could have arbitrarily small type 1 plus type 2 error. This could be exponential if we want it. And okay, this is a little bit convoluted, but the conclusion is that it is unlikely that there is a polynomial time estimator, given that we know that this class of spectral methods are really powerful, and this implies that no spectral method would solve our problem. All right, so that's one piece of evidence. The second piece of evidence, theoretical evidence, is this semi-definite relaxation. Let me quickly go over this. This is sort of an idea that people had at the beginning of the 2000s, where they realized that actually we can rewrite the Max-Cut problem as a linear program, where since the trace is invariant under cyclic permutations, actually you can write everything as maximize this linear form, where this is H the original one, and this y is now my a matrix of variables of n times n variables, and I'm going to restrict the y to be in some polytope, which is the convex hull of every rank 1 matrix y transpose with y in the hypercube. This is a linear programming problem, and in particular, this guy has a name. Whenever you have a name, that means that you're very hard, and so it's actually hard to optimize over this cut polytope. But people realize that maybe, although this problem is hard, we can take a relaxation of this set that is nicer, that we can use optimization software to optimize over. This was the idea that Gaussians and Williamson had in '95. Instead of considering the original problem, they consider every matrix in here has to satisfy that, well, it is positive semi-definite because it's a convex combination of positive semi-definite matrices. And moreover, the diagonal of the matrix has to be 1. Again, convex combinations of matrices with diagonals 1. This is larger than the original cut polytope, but it turns out that it has a nice description that we can use because this is an SDP that we can optimize over in polynomial time. It turns out that you can actually generalize this idea and have sums of square relaxations. This is an idea that is due to Parolillo and Lasserre. They both independently came up with it, where essentially instead of just thinking of one relaxation, you look at tighter and tighter relaxations of the same object. So you can imagine this is the first relaxation, and then I get tighter and tighter relaxations, and finally I get the polytope here that is really hard to optimize over. There is a very nice interpretation that I don't have time to go over in terms of moments of information, but the idea is that if you were to fix the level here, say level 2 or level 4, for each fixed level, I can optimize over this. I can solve this optimization problem in polynomial time and obtain a bound for the true optimization problem that I'm interested in. This strategy has proved to be extremely successful in machine learning and dynamical systems and control and theoretical computer science. So it's natural to wonder whether this could give a solution to our problem. Unfortunately, we proved a lower bound that I think I'm already almost going over time, so I'm not going to go into too many details. But the general idea of the lower bound is that there always exists a solution for a fixed level that is statistically independent of the true labels. So intuitively, this is saying that when n grows like d to the power of 3/2, any relaxation of a small degree has a solution that performs pretty much as a random guess. This is slightly weaker than what we proved for the other result, but nonetheless is evidence and is based on an obstruction obtained by Gauss and others in 2020. So just to summarize the talk, we introduce a statistically optimal procedure that gives you base optimal error with near linear sample complexity based on this combinatorial optimization problem over the hypercube. We came up with a computationally tractable procedure based on the spectral methods and alternating projections that yields optimal error, yet requires quadratic sample complexity. And finally, we conjecture that there is this statistical to computational gap, and that between d and d squared, there is no hope to have a computationally tractable method that would answer the question of clustering. So that's all I have today. Thank you very much.
Well, thank you, Professor Díaz, for the great talk. Any questions? Thanks, Ben. Yeah.
Well, maybe the online.
Online people?
Yeah, first.
Yeah. Go ahead. Yeah.
Thank you for the talk. It was very interesting. Could you please tell me what is a planted vector in the definition of the hard hypothesis testing?
Yes. So is it here? Yes. When I said planted vector, you can think of this as I have a matrix where everything is Gaussian. So it doesn't really matter if I apply an unknown rotation to this x as well. I could multiply by q here as well. And I would still have the same distribution, right?
Yes.
So what I'm doing here is I'm considering a planted vector where I substituted one of the Gaussian vectors that is generating everything by a vector of ones and minus ones, and then I'm mixing everything again using the q so that we don't know whether or not that vector was there. So that's what I mean by a planted vector.
Is it assumed to be a random vector, this y star, or is it a fixed?
You can make it a random vector if you want. It doesn't really matter. It can be fixed or random. All of these results are proven assuming that it has any distribution you want. So it could be random, but the distribution could be also an atom that is just fixed, and so it's a deterministic thing. So anything is fine.
So basically, the idea is that it is hard to distinguish between really Gaussian matrix and the one which is like one column of which is not really a Gaussian.
Yes.
Yeah, I have a couple of more questions if possible.
Yes, go ahead.
Yeah. So if I understand correctly, the sample complexity of the expectation maximization that you showed using that heat map was also quadratic, right? Because the slope was also 2.
Yeah.
So does this mean that EM is doing more or less, I mean, EM does the job more or less as well as what you suggest?
Yes. I should remark that none of these algorithms have any theoretical guarantees. And it took us a while to prove the theoretical guarantees for the spectral plus alternating projections. This is a very delicate problem to analyze. Sorry?
Could you please repeat the last remark?
Oh, yeah, I'm saying that all the other algorithms that we consider here have no guarantees. So these are the first theoretical guarantees for this problem, if you consider the stretch case.
Oh, I see. So basically, EM empirically does the job well, but there is no theoretical guarantee that it will find the global optimum.
That's correct, yeah.
Right. Okay, and last question is, for the sake of fair comparison, did you initialize EM the same way as your approach, or was it initialized?
If I remember correctly, we initialized EM like multiple times and took whatever gave us the best result.
Yeah, in practice, EM is usually initialized with k-means, right? I mean, at least the filters are usually initialized with k-means. And if we look at one of your examples where k-means gave terribly bad classification, then EM could be in a bit, inferior position compared.
Right. Yeah. So I think what we did was we first tried k-means. We saw that it was terrible, and so we decided to initialize at random. And I don't remember how many we tried, but I think like 10 initializations at random or something. Okay. And then whatever gave us the best result.
Thank you. It was a very interesting talk.
Other question.
Thank you.
So all these results are, the groups have the same variance, right?
Yes, they have the same covariance, yeah. We have in the paper, okay, let me say that the reason why I'm presenting here this simplified case where we have the same covariance is just everything is easier to see and the results are the strongest that we have. But in the paper, we have results with arbitrary covariances. It's just they're slightly weaker. But the interesting part here is that we obtain this sort of sharp phase transition and the statistical to computational gap, even in the simplified case. So it's just really hard, even in the simplified case.
Okay. And what about results with different weights on the type 1 and type 2 error?
Yeah, that's solved in the paper. We have the more general case with an arbitrary number of clusters and different weights and different covariances in the paper.
Okay. So another thing that I've seen relating the MaxCut problem with tools from PD. So
Okay.
yeah, I don't know if you've seen those type of work, like which they were connecting to Ginsburg, Landau, functional, and all this type of thing. Have you?
I'm not extremely familiar with it. No.
That might be a good comparison.
I should say that there are many algorithms to solve this.
Yeah.
We just picked the ones that we thought were the most popular in data science and tried to use them.
Yeah.
Yeah.
Awesome. Other questions? Well, if not, let's thank Professor Díaz for the great presentation. So thank you very much.
Thank you. Thank you for the questions.
Thank you. And I guess we'll resume tomorrow at this point. Okay. So thank you.
Cool. Bye, everyone.